We will begin with the final chapter of this course, okay, which is operational amplifier part 1. Okay, for the part 1 is the linear linear op-amp. Okay, part 2 later will be on the non-linear op-amps. Okay, the short form for operational amplifier is op-amps. Okay, the scope is the op-amp characteristic. Okay, of course the IV characteristic. Okay, and the linear application. Okay, for this one, part 1 linear application, we have inverting, non-inverting amplifier, voltage followers, summing amplifier, and subtractor amplifier. Okay, we're going to look all these types of linear application, and we will derive the equation. Okay, so usually called as an op-amp. Okay, an amplifier is a device that accepts a varying input signal and produces a similar output signal with a larger amplitude. Okay, usually it is connected so that the part of the output is fed back to the input, means that it has feedback resistor. Okay, most of them behave like a voltage amplifier. Okay, amplifier, same like what you have done in the BJT and MOSFET. Okay, that is the amplifier as well. So op-amp also used as in voltage amplifier. Okay, they are the basic component used to build up analog circuits. Okay, the op-amp. So the name itself, operational amplifier, comes from the fact that it is used to perform mathematical operation such as integration and differentiation. Okay, so integrated circuit fabrication technique have made high performance op-amp with a very inexpensive in comparison to the older discrete devices. Okay, so op-amp, the characteristic, it has a very high gain. Okay, gain differential amplifier. Okay, voltage gain very high with high input impedance. Okay, the Z in is high, but the output has low output impedance. Right, so this is the main characteristic of the op-amp. Okay, so note that the op-amp has two inputs. Okay, so this is the symbol for op-amps, a triangle symbol. So it has two inputs with positive inputs and negative input. Okay, and it has only one output. Okay, so this is just the simple symbol of op-amp. Okay, but it may have a feedback resistor. Okay, from output to the input. Okay, we will look to it later. So this is the typical op-amp. So this is how it looks. So op-amp is made up, is look like an IC. So this is op-amp actually. So we have several type of op-amp. For this case, the type is MC1741 CP1. So this is the type of op-amp. So op-amp has for this one, it has 8 legs or 8 terminal. 1, 2, 3, 4, 5, 6, 7, 8. So each of the pin here represents different voltage. Okay, so in here, if you look here, so for this inside this IC, op-amp IC, so it has pin 1, 2, 3, 4, 5, and 6. So you have to connect each of the pin correctly in order for your op-amp to function. Okay. Okay, op-amp has a very high gain, so they can be connected open loop or closed loop. For example, for open loop, okay, this means that your connection of this circuit, okay, so you can arrange this circuit connection can become open loop or closed loop. Okay, depends of the resistor you applied and the voltage supply you applied, so on. Okay. All right, so for the open loop, okay, refers to a configuration where there is no feedback from output back to the input. Okay, in the open loop configuration, the gain can exceed 10,000. Okay, for the closed loop configuration, it reduces the gain. Okay, in order to control the gain of an op-amp, it must have feedback. Okay, feedback. Feedback means, okay, from now you have input and output, and then you have output, which is it is not connected to each other. But feedback means you can connect between input to output with a resistor feedback, okay, with a feedback resistor. All right. So a negative feedback reduces the gain and improve many characteristics of the op-amp. All right. So this is how it looks. Okay. So in op-amp, it has two input. Okay. The negative input and also the plus input. The name for the negative input, we call it as an inverting input. Okay. Inverting input. So whatever the output from this negative will be invert. Okay. So it has inverting input, and also the plus one, we call it as a non-inverting input. So inside here, from the inverting input, it has current inverting, which is represent as I negative into your op-amp. Also, from the non-inverting input, you have current I plus, okay, which is going into the positive pin of your op-amp. Finally, you have voltage, okay, V out. So this V out is equal to the gain of this op-amp. Okay, as you know, your amplifier, the one that you have done in BJT and MOSFET, is to find the gain. Okay, so that gain is used to amplify the signal of the output. Okay, so V out is equal to the gain times the V in. Okay, in this case, since it has two V in, okay, your BJT and MOSFET, there's one V in. Therefore, V out equal to A V in. But in this case, V out is equal to the difference input of the V in, because it has two input. Therefore, the voltage is different at the input. Okay, so op-amp, okay, one of the pins, just now it has 8 pins. So one of 8 pins, it must be connected to voltage supply. Okay, voltage supply. So this is the input of the op-amp, but your op-amp must be supplied with power. Okay, so you have to supply positive VCC and negative VCC. All right. So plus minus usually 15 volt. Okay. Plus 15 volt and minus 15 volt. Okay. The rest inside this is the internal impedance. KA is the gain. R out is the output impedance, and so on. All right, so this is the op-amp transfer curve. Okay, since this is a linear, okay, linear application, so as you can see, the V out versus V plus minus V minus. Okay, so this one, if I can draw this, so this is your V out, the output. Okay, okay, and this is your V minus. This is your V plus. Okay, usually V minus is the inverting input, V plus is non-inverting input. Okay, therefore this V out is actually the gain here. Okay, multiply with the difference. Okay, this V in D means V in difference. So in this case, it is equal to the V plus minus V minus. All right. Okay, so you know that gain is equal to the V out over V in. In this case, V in has two input, V plus and V minus. Therefore, V in is the difference. Okay, so this is the transfer curve. Okay, linear. Why it is linear? So between output to input, so this is equal to the V in. Okay, the difference. Okay, V plus minus V minus. Okay, so it is actually linearly dependent. Okay, linear dependent. So that's why this case of M is called as a linear application, where the V out, okay, the V out is equal to the gain times V plus minus V minus. Okay, but the op-amp characteristic, okay, so since it is linearly dependent, okay, linearly dependent, but it has limit. So for how long it is for how much it is will be linearly dependent. So it is it has a saturation point. Okay, it has a saturation point. So what are the saturation point is how much your voltage supply applied. Okay, this one. So it will be limited or saturated to the your power supply of op-amp. Okay, the voltage power supply. Okay, it cannot be greater than the power supply applied. Cannot be. Okay, it will be saturated to the plus minus V power supply. Okay, so this is the op-amp transfer curve characteristic. So in order to analyze your op-amp, so for the ideal op-amp characteristic, okay, it has high open loop gain where the gain is almost infinity, and it has a high input impedance, low output impedance, and the output saturation voltage is plus minus V out saturation. Okay, so this is what it meant. Okay, plus minus V out saturation. So this is V out saturation plus this is minus V out saturation. Okay, and other than that, there is another terms called CMRR, okay, common mode rejection ratio, which is this is related to the ability of op-amp to reject unwanted noises, unwanted signal. Okay, so op-amp has high ability to reject unwanted signal or noises. Okay, so op-amp is good if you have if you listen to music. Okay, sometimes you heard noise, so how to avoid to eliminate these noises or unwanted signals in the system, in the amplifiers, in the amplification system, usually they use op-amp. Okay, and op-amp also has high bandwidth, okay, approximately to the infinity. Okay, so other than that, op-amp specification. So op-amp is widely used in wide bandwidth amplifier. Okay, so the following affect the bandwidth. Okay, it has two. One is gain. I think you all know. Okay, V out equal to gain times V in. The other is slew rate. Okay, what is slew rate? Let's take a look after this. Okay, op-amp is widely used, which is it is stable for the high frequency application. Okay, so if you have bandwidth previously like this, okay, so usually here you can use BJT or MOSFET. Okay, this kind of amplifier that you have learned, which is stable, okay, for the low frequency application. But most of the time, for the high frequency application, people use op-amp instead. Okay, right. So is the maximum rate at which high frequency application, this means sometimes up to gigahertz. Okay, gigahertz. Okay, for BJT and MOSFET you can use maybe up to megahertz, but if you want to for wide bandwidth application up to gigahertz, okay, usually we use op-amp. Okay, in the maximum slew rate, okay, slew rate rating is given in the specification sheet as voltage over microsecond. So is the maximum rate at which op-amp can change output without distortion, or it is actually the limitation of maximum possible rate of change of the output to an op-amp. Okay, slew rate is independent of the closed loop gain. Okay, slew rate is another parameter which is equal to the difference of voltage over time. Okay, how much the voltage can change, okay, over time. So is it fast? If it is need more time, means the slew rate is high. If it is need less time, then the slew rate is low. Okay, so the maximum signal frequency. Okay, the slew rate determines the highest frequency of the op-amp without distortion. Okay, so frequency must be less or equal to the slew rate over 2 pi Vp. Okay, for example, if you have an op-amp with the slew rate 0.5 volt per microsecond, Okay, so what is the maximum frequency before the distortion occurred? So this is how you calculate. So F less or equal than the slew rate over 2 pi over V peak. If V peak is given 15 volt, therefore the frequency, okay, the maximum frequency occurred before the distortion is 5.3 kHz. Okay, so slew rate limitation. So this is your desired output waveform. Okay, desired output waveform. If you have input waveform sinusoidal, your output waveform must be also sinusoidal. Okay, because of the slew rate, so the actual output may look like this. Okay, instead of sinusoidal, you may get a triangle. So this picture is actually shows exactly what happens when the slew rate limitation not met the specification. Okay, which means that the output of the operation amplifier is being distorted, or it has many noises. All right. Right. So, sorry. Okay, so the amplifier properties, ideal versus non-ideal. Okay, for the ideal, it has infinite gain, infinite bandwidth, infinite input impedance. But in non-ideal, or in real case, it usually have like 10 to power of 6 gain, 1 megahertz, and 100 mega ohm for the input impedance, and so on. So this has the several applications. So for example, for the high gain, it can be used for the microphone. For the high bandwidth, it can be used for ultrasound. And the example for the high input impedance can be used as a piezoelectric crystal. For the output, low output impedance is for the loudspeaker. And this is the application for the medical, okay, medical application. Okay, so the op-amp, the advantage of op-amp, it has no external element is needed for the stability. Okay, the gain value varies with feedback to one of the input. Okay, AC signal can be amplified without biasing, and the output nearly zero when input is zero. Yes, and the output can be in phase of 180-degree out of phase with the input. Okay, how you want to analyze your op-amp. Okay, there is a basic and most common circuit building. Okay, ideally, so this is your symbol of op-amp. Like I said, it has negative input. This one is inverting input, and it also have positive input. This one is non-inverting, and you have V out. So V out is equal to the A gain times the difference of input. Okay. So in ideal case, so every time if you want to analyze your op-amp, okay, you must have to consider for the ideal case. Okay. Okay, so no current can enter terminals. So this one, there will be no current enter here. So means that there will be current. If there is current enter this op-amp, this current negative, I negative will be equal to 0. I positive will be equal to 0. Okay, this one we call it as an infinite input impedance. Okay, we will look after this. Okay. All right. So in this case, this is what it meant by this one. So you have I negative. Okay. So I inverting equal to 0 and I non-inverting also equal to 0. Okay. Current cannot enter the op-amp, which is equal to the 0. Okay. So V out is equal to the gain times the difference of input voltage. And number 3, in a circuit, V plus is forced equally to the V minus. Okay. So in this case, V plus is equal to the V minus. Okay. For this case, current cannot enter means that I equal to 0. I negative equal to 0. I plus equal to 0. Okay, and this one we call it as a infinite input impedance. The second one, V plus must be equal to the V minus. This one we call it as a virtual ground. Okay, and op-amp needs two voltages, okay, VCC minus VCC, which is this one, the voltage supply. Okay, and this called as a rails, or the rails voltage, because it has the same magnitude, bit different plus minus. Okay. Okay, the key to op-amp analysis is simple. Okay, there is no current can enter, means that this one negative, I negative equal to 0, I positive also equal to 0. Okay, that is the first term you need to know to analyze op-amp. Okay, and also the positive and negative nanometer sample. Okay, so this one number 2. V plus must be equal to the V minus. Okay, means that V non-inverting equal to the V negative, B inverting. Okay, this property is called as a virtual ground. Other than that, we use this ideal op-amp property in the analysis. Okay, only these two will be used in order to analyze your op-amp circuit. Okay. Let's take a look on the example. Okay, so we have inverting amplifier. So inverting amplifier means that at this node, okay, like I said, V at negative, okay, at negative we call it as a V inverting, V minus, and this is V plus. Okay, so for the non-inverting amplifier, for inverting amplifier, means that the input voltage, okay, this one is the input voltage, okay, the input voltage, for example, V1, okay, this input voltage is connected to this negative input of op-amp, to the inverting input of op-amp. Therefore, this amplifier, we call it as a inverting amplifier. Okay, when your voltage supply V1 is connected to the negative, then this is inverting amplifier. All right. So other than that, okay, in order to make it this op-amp become closed loop, it has feedback resistor. Okay, so this is the feedback resistor where it connect between output to the input. All right. And also the non-inverting input, which is the V plus. Okay, the V plus is connected to the ground. All right. And the RF is feedback resistor. So it is the connected of the output. This one we call it as a negative feedback. Okay. Why negative feedback? Because the resistor feedback, okay, the feedback resistor is connected from the V out to the negative input of your op-amp. This one we call it as a negative feedback. Okay, yeah, other than that, this, okay, let's, I think, better look at the example. Okay, so there are practical op-amp circuit. Okay, so in this case we have 5 types. Okay, the voltage follower, the inverting amplifier, and the non-inverting amplifier. Okay, the fourth one is difference or substructure amplifier. The final one is the summing amplifier. Good. So this kind of different op-amp circuit has different connection for the how it connect the op-amp circuit is different. Okay, so how we analyze the circuit also different. Okay, we're going to look through one by one after this. Okay. All right. So only two things need to be clarified, or we will take into consideration in analyzing all the 6 types just now. Only two, which is one, we apply infinite input impedance where I negative equal to 0, I plus equal to 0, and we apply the virtual ground, ideal virtual ground, which is V plus is equal to the V minus. Only these two. Okay, so let's take a look on the example. For the example 1, okay, for the number 1, which is the voltage unity, okay, voltage follower. Okay, so for this one, you have op-amp, you have no resistor, you have input, okay, to the V plus, and V minus is connected to the V out. Okay, there is no resistor. Okay, we know that we take the second analysis, which is this one. Okay, V plus is equal to the V minus. Okay, V plus is equal to the V minus, where the V plus itself is equal to the V in. Therefore, your V out, since there is no resistor, V out is connected directly to the V minus. Okay. Therefore, V out is equal to the V minus equal to the V plus equal to the V in. Okay, for this case, it is very straightforward. Okay, usually we want to take your V out equal to the V in without any noise. So we use the type of unity follower amplifier. So basically, V out is equal to the V in. That's it. Okay, so why we use OPAMP? Because we want to get the exact input. Okay, your V out must replicate the exact input of the V in without any noise. Okay, so this is very useful for the interfacing to high high impedance, such as for the sensor, microelectrode, and also for the microphones. All right, so the second one, inverting amplifier. Okay, let's take a look over here. Okay, before that, I wait, need to add one more slide. All right, okay, let's take a look over here. So for this one, this type, okay, if you look at here, inverting number second is inverting amplifier. This one, inverting amplifier. Okay, so how the circuits looks like from the name itself. Okay, it is inverting. Okay, therefore your V in, okay, is connected to the negative of op amp. Okay, but in this case V plus is connected to the ground. Okay, that's why this one we called it as an inverting amplifier. Why we call it as an inverting amplifier? Because the input voltage is connected to the negative negative op amp, negative V minus. Okay, so how to analyze this is by using a virtual ground, which is V minus equal to the V plus. Okay, so I think I better write down again, okay, so that you know. Okay, let's do it. So in the end of the day, you want to derive what is the V out. Okay, so this is the objective of op-amp. Okay, because we want to find the gain. Okay, the objective to analyze all the type of circuit here is to find the V out is equal to what V in. Okay, because you want to find the gain. Okay, the gain, which is V out over V in. So this is your objective. Okay, so let's take a look on next here. Okay, let me draw first the circuit. So wait, I need to yeah, I draw it here. Okay, so this is your V1 R1. Okay, and this is your V out. Okay, for this case, I want to put this as a feedback resistor. Okay, this is minus, this is plus to the ground. Okay, all right. So that's it. Okay, so the key to solve this is two. Okay, one, you need to know that I think better for you to write everything here. So you have this one is V minus, this one is V plus, and the current going here is I minus, current going here is I plus. Okay, you need to take both both assumption. Okay, which is the first one is I minus, and sorry, the first one is the virtual ground, which is V plus equal to the V minus. The second one is I minus is equal to 0, I plus is equal to 0. Okay, so this is the two assumption that you need to take into consideration in order to analyze it. Okay, so let's make this as the current here is IRF. Okay, so the current here, I make it as IR1. Okay, okay. So now I want to make the KCL at this node. Okay, KCL at this node. Okay, at that node A. So KCL at node A is equal to, when I say KCL, means that total current in is equal to the total current out. Okay, so what is the total current in to the node A? So you have current IR1. Okay, do you have any current in going to the node E? Yes, you have IRF. Okay, you have anything other than that IR1 and IRF? Nothing more current in, but you have current going out from the node A, which is I minus. All right, so I minus is equal to 0. Okay, so this equation IR1 plus IRF equal to 0. Okay, if you take KVL, okay, IR1, okay, IR1. So in this case, IR1 is equal to the V1 minus V minus over R1. Am I right? Yes. Okay. And IRF is equal to the V out. Follow the arrow. Since it's the arrow from left, therefore V out minus V minus over RF equal to 0. Right? So if you take the first assumption, okay, the first assumption, which is V plus equal to the V minus, okay, so now V plus is equal to what? My question.
0.
0 because it is grounded. Okay.
Grounded.
Yes, correct. So V plus minus equal to the V plus. So in this case, V plus equal to 0 because it's grounded. Therefore, V minus equal to the V plus equal to 0. You can simplify this equation. So it is equal to 0, 0. Okay, the equation now become V1 over R1 plus V naught over RF equal to 0. Okay, so if you rearrange the equation, you should get that V out is equal to the negative RF. Sorry. Okay, over R1 V1. Okay, so V out over V1 is equal to the negative RF over R1. So it is makes sense because the V out is connected to the inverting, which is negative. So this is your equation that you should find. Why I ask why, you can memorize, but no, don't memorize because in final exam there will be more resistor involved. Therefore, you derive it. Okay. The key to derive for op-amp, just these two things. Okay. Apply KCL. KCL to notes. Okay. And also you apply these two. Okay. These two assumption. Okay. V plus equal to the V minus. I minus equal to 0 and I plus equal to 0. And then just KCL. Just KCL. Okay, so now is it right? So in the slide said V out equal to the negative R2 over R1. So in this case, your R2 is RF, R feedback. So it is the same thing. Okay, V out is equal to the negative RF over R1 V in. Same like I have derived here. Okay, so this is for the case of inverting amplifier. Okay, inverting amplifier. Okay, so the next one is non-inverting amplifier. Okay, non-inverting amplifier. Okay, we will derive all first and then we will look um, at the example. Okay. Um, okay. Alright, so for the non-inverting amplifier, why does it call as a non-inverting amplifier? Okay, sometimes they ask you to determine the names of that amplifier. So my question is, why the name is non-inverting amplifier? Can someone give me the answer? Why non-inverting amplifier? Hello?
In connect to plus.
Yes, okay, V in connected to the V plus. Okay, therefore this is non-inverting amplifier. If it is inverting, means V in connected to the V minus. The output is invert to the input. Okay, so we expect that this output is not invert. Okay, because it is connected to the V in connected to the plus. Okay, plus. All right. So again, okay, to solve this, okay, is easy, okay, by applying KCL and then by using two assumption, V plus equal to the V minus and also current equal to 0. Okay, let's derive it together. Okay, I have to draw the circuit first. Okay, I'll draw it here. Okay. Okay, so this is the circuit given. Okay, all right. Okay, first thing is V plus is equal to the V minus. Okay, in this case, you have here V plus and you have here uh, V minus. Okay, the second one, okay, in this case, when V plus equal to the V minus equal to what actually? Equal to what? Equal to V plus equal to the V minus equal to what? V plus equal to what?
V in.
Yes, the same note here. So it is equal to the V in. Okay. Okay, you have to write down everything. So I plus is equal to 0. I minus equal to 0. So where is I plus and I minus? So this is your I plus and this is the F for I minus. So this current 0, this are equal to 0. Okay. Now I have to apply KCL. Okay, KCL at node A. Okay, at this node. Okay, at this node. Okay, KCL at this node. Okay, so we make current. Okay, so you have current here, which is IR, and you have here current IR1. Okay, so KL is equal to the total current in is equal to the total current out. So what are the current in to the node A?
IRF.
Yes, IRF. Okay, is there any current in anymore?
No.
No. Okay, so what is the current out here?
R1 and I negative.
Yes, correct. IR1 plus I negative. So in this case, I negative equal to
0.
0. Correct. Okay. So the equation left with IRF equal to the IR1. All right. So now IRF is equal to what? IRF. So I want to, yeah, IRF. Can I write it? Oh, yeah. So it's going to be long. Okay. So I will jump to here. So IRF is equal to what? Can you give me what is IRF?
V out minus V negative over RF.
Yes, V out minus V negative. So along this node is V negative. Okay. Over RF. Okay. Equals to, how about VR1?
V negative over R1.
V negative over R1. Anything else? Nothing else. Okay. So if we rearrange the equation, so I want to replace V minus. Okay. So V minus now is equal to what? So V minus equal to the V plus.
V
If
in.
we take this, also equal to
V in.
V in. Okay. So this equation, if I rearrange, I will get that V out minus V in over RF equal to the V in over R1. Okay. Therefore, V out over RF is equal to the V in over R1 plus V in over RF. Okay. So this one will be V out over RF, okay, is equal to the V in 1 over R1 plus 1 over RF. Okay, if I take the everything RF go there and V in to the below, you will get V out over V in is equal to RF over R1 plus RF over RF is 1. Okay, therefore this is your derivation. Okay, so let's take a look on the slide. Is it same? Yes, it is same. So V out is equal to 1 plus R2 over R1, where your R2 is RF now. Okay, R feedback. Okay, why I use RF? Because sometimes in the test and sorry, not test, in the final exam they use feedback resistor, okay, RF. So it is the same thing, okay, just the name, the notation. So 1 over R2 plus R1 times V in. Same thing here. RF over R1 plus 1. Okay, the same thing. If I write down here again, so V out equal to the V in equal to 1 plus R2 over R1. Okay, the same thing. Okay, so why I derive this? I can say that this is not a hint or tips. In the final exam, they will ask you to derive first and then calculate. Definitely, there will be a question for you to derive first and then calculate. So that's why I show you how to derive. Okay, but the derivation is simple. Only two things need to be considered. Okay, V plus the virtual ground, which is V plus equal to the V minus, and also the high input impedance where no current can enter the op-amp, where I plus equal to the 0, I minus equal to the 0. And then you apply KCL at any node you want. Okay, in this case at node A, which is node inverting. All right, so what is the third one? So we've done 3. Okay, the third one is a difference amplifier, but in my slide comes first the summing amplifier, so we will look at the summing amplifier first. Okay, So summing amplifier, so this is how it looks like, where the input, in this case, it is summing inverting. Okay, why summing inverting? Because the input, as you can see, the input over here, okay, is connected to the negative op-amp. That's why this is summing amplifier for inverting. Okay, so as you can see here, summing, because there is a summation of input voltage. Okay, in here it has V1, V2, and Vn. Okay, Vn is could be V3 or it could be more. Okay, so how you derive this? Again, you will have to apply the assumption just now and also the total voltage, right? Okay, so let's take a look over here. I need to add one more slide. Okay, so yeah, you have, in this case, your V in is connected to the V minus. Okay, and this is your V plus. Okay, I better, so you have Vn instead. Let's do it. Now I want to draw at the left lah, pula here, like this. Okay, so you have your input here. Let's make the input only 3, V2, R2. And then you have V3. This is V3. The other one is V1, R1. Okay. And the ground, plus, minus. Okay. And of course, you have the RF. All right. Okay. All right. So you have to write down everything so that you won't be forgetting. I think it's better to write all the notation. You have V minus, and then you have V plus over here, and then you know that the current negative here equal to 0. Alamak, tak cukup. So this is V plus, so current here 0, and current here also 0. Okay, all right, so two assumption made. Okay, write down everything so that you know. Okay, so two assumption made, which is V plus equal to the V minus, and number 2, no current can enter. Okay, I minus equal to 0, I plus equal to 0. In this case, V plus equal to the V minus equal to 1. So, hello? So V plus equal to the V minus equal to?
0.
Yes, 0. Why? Because your V plus is connected to the ground. V plus equal to 0. So this one equal to 0. Okay. Now I want to take the KCL at this node. Okay. At this node. At this node. Okay. Node A. Okay. KCL node A. Okay, so you have to create the current. Okay, create the current. You have here IR1. Okay, and then you have here IR2, and then you have here IR3. Okay, not to forget, you have IRF, the feedback. Okay, so now the KCL at node A. So let's write down. So KCL means the total current in is equal to the total current out. Okay. Now tell me, what is the total current in at node A? What current you have there?
IR1, IR2, IR3.
Yes, IR1 plus IR2 plus IR3. What else?
IRF.
Yes, IRF. Equal to I negative. Yes. Now I negative equals to 0. Correct. Okay, equal to 0. So you write down again what is IR1, IR2. Okay, so in the exam, there must be a number lah, of course. So you put the number. So first thing you have to derive, because they definitely ask you derive. Okay, later when I give you tutorial, then you can see. So this is a compulsory question, need to be answered in the final exam. Okay, OPAMP is question, OPAMP linear is question number 3, question number 3. Okay, so V1 minus V minus over R1 plus V2 minus V minus 2 over R2 plus V3 minus V minus over R3 plus VRF is V naught over V minus over RF equal to 0. Now, what is V minus? What is V minus? V minus equals to what?
0.
0. Okay, 0. 0, 0, 0, 0. So this equation left with V1 over R1 plus V2 over R2 plus V3 over R3 plus V out over RF equal to 0. Okay, if you rearrange the equation, you should get your V out is equal to the negative RF times V1 over R1 plus V2 over R2 plus V3 over R3. Okay, so this is for the case of where you have 3 input. Okay, if you have 5 input, then you have V4 over R4 plus V5 over R5. Okay, so let's take a look here. Is it the same? Yes, it is the same. Okay, V out is equal to the negative R1, V1 over R1, and so on up to Vn over Rn. Right, so this is how you derive the summing amplifier. Okay, yeah, definitely worth for to derive it. Okay, so for the second one, okay, we will take 5. Okay, and I will ask you to derive this on your own. Okay, after take 5, you take 5 first. Okay, and then you try to derive this one. Okay, until you get the V out equal to 1 plus RF over R1. Okay, we take 5, right? Hello? Hello? Okay, we take 5, right? After take 5, you can try to derive this, okay? Hello? Okay. So, yeah. Okay. So for this one, hello? And there? Okay. So summing amplifier, this one for non-inverting, okay, non-inverting, where the output is connected to the, sorry, the input is, yes.
Hello?
Hello?
Yeah, we can't hear you well because you're like too low. Yours.
Oh, my voice cannot hear me?
Yeah, yeah.
Yes.
Oh. Give me a second. How about now? Hello? Okay, great. Okay, so summing amplifier, non-inverting, okay, where the input voltage is connected to plus, okay, the non-inverting point. Okay, so all right. So now can you try to derive? I give you 5 minutes to derive it. Okay, so the tips is you have to use the assumption V plus equal to the V minus, and also I minus equal to the I plus equal to 0. Okay, so take the assumption. So number one assumption is V plus equal to the V minus, and number two, I plus equal to 0, I minus equal to 0. Okay, so where you should do the KCL, okay, so you have two, okay, first, actually you have two node to apply KCL, okay, at this node and also at this whole node, okay, this node. Yep. Okay, if you write down everything, then you'll be much clearer. So you have here I minus equal to 0. Okay, this one you have I plus equal to 0. Okay, I give you 5 minutes. Okay. Did you manage to get the derivation? Where is my mouse? Did you manage to get the derivation? Any of you? Not yet?
Wait,
Okay. All right. Okay. Before that, I need to add my slide for derivation. So need to copy because I'm lazy to draw. Okay. So wait. All right. So let's do together. Okay. I think you are halfway there. Okay. You want me to show you how to derive it, or you get the derivation? You can derive. Hello? You want me to show it to you or not?
Yes, Doctor. Please.
All right. Okay. Maybe stuck somewhere. That's fine. Okay, let's do it. All right. Sorry, kuat sangat. Okay, so you have okay, write down everything, blah blah blah, whatnot just now. So many, right? So V plus equal to the V minus. Okay, number 2, I plus equal to 0, I minus equal to 0. Okay, you have here I minus equal to 0. Here, I plus equal to 0. Okay, so you have two nodes. Okay, so I better highlight it here, node 1 and node 2. Okay, now let's do sorry. You have here I RF. Okay, and then you have here I R1. Just made up your current direction. Doesn't matter to the left or to the right, as long as you put the correct KVL rate later. Okay, all right. So you have here IRA. Okay, and IRB. Okay, all right. Okay, so now let's do KVL. Okay, KCL at inverting node at node V minus. Okay, at node V minus. All right. So current in equal to the current out. So what is current in?
IR1 plus IRF.
Yes, IR1 plus IRF equals to?
I minus.
Yes, I minus. This one, I minus equal to 0. Okay, write down what is your IR1 and IRF. So IR1 is 0, ground from ground, minus V minus. Okay, over R1. Okay, IRF V naught minus V minus over RF. Okay, here you should get that if you
Sorry,
combine,
Doctor.
yes,
Why IR1 is dekat I in? Kenapa dia tak go to the ground?
one more time, Edlan.
IR1 tu
Mm-hmm.
dia dekat some of I in, right?
Mm-mm.
Kenapa dia tak dekat dia punya arah dia ke ground? Sebab dekat
Like this, macam tu. Like this.
sebab dekat non-inverting dia punya arah dia dekat ground. R1.
Oh, okay. Idlan, doesn't matter. If your current direction IR1 to the left, that's okay. So therefore, if your IR1 to the left, okay, let's say your IR1 like this, okay, doesn't matter. So it is actually current going out. So it will be in this here, dekat sebelah sini lah. Kat sebelah sini. Therefore, dia akan jadi at the right side because it's current out, like not current in. Now I make it current in. But if you want to make it to the left, and that will be your current out from that node. Therefore, the equation will be V minus 0 over R1. Okay, so portion ni, this portion, no. Okay, there will be no this portion. So your equation will be like this. Okay, doesn't matter. Okay, like I said just now. So current direction doesn't matter. Okay, you decide your current direction, but later when you want to write the KVL must be correct. Okay, if my current direction now is to the right. Okay, to the right. Okay, this is my current direction to the right. Therefore, my current from 0 ground to minus V1 over R1. For example, Idlan just now, the current direction is to the left. Therefore, Idlan current direction is I out V minus 0 over R1. Okay, doesn't matter. You decide your current direction, but when you write the KVL, must be correct. Doesn't matter. Is that answering your question, Idlan?
Okay, thank you, Doctor.
All right, welcome. Okay. Sorry. Okay, wait. I need to. Where is my? Sorry. 5 seconds. All right. Okay. So for this equation, okay, if you simplify this equation, you will get okay, V out over RF, okay, minus V minus. Just simplify the equation. 1 over R1 equal to 0. Okay, and therefore, finally, your equation will be okay, V out over RF equal to the V minus, okay, V minus 1 over RF plus 1 over R1. All right. So now your equation V plus is equal to the V minus, right? V plus equal to the V minus. Okay. Therefore, this equation will be V out. Can I write like this? RF. Okay. Okay, I take this, I replace V minus equal to the V plus because this equation they make in the terms of V plus. Okay, it is the same thing. Okay, therefore, it is actually V plus RF over RF plus RF over R1. So this equation will be V out, V plus 1 plus RF over R1. Okay, so now we got the first term over here. All right, so next one is to apply KCL at node V minus pula. Sorry, just now, V plus. Okay, sorry, V plus. So just now we make KCL at node V minus. Okay, now you have to make KCL at node V plus. Okay, give me 5 seconds. Yep, sorry. Sorry for the interruption. Okay, now KCL at node V plus. Okay, KCL at node V plus. So like I said, your current direction doesn't matter. Up to you. As long as when you put the KVL is correct. Okay, so so current in is equal to the current out. Okay, current in is IRA. Okay, plus IRB equals to the I plus. Okay, in this case, I plus equal to, hello?
Zero.
Hey, anybody there? Okay. Right. So IRA is VA minus VA minus V plus over RA plus VB minus V plus over RB equal to 0. Okay. All right. So from this equation, so you can actually simplify it. Okay. So your equation will be let's make it like this. So VA over RA plus VB over RB is equal to the V plus. You take the other side. So 1 over RA plus 1 over RB. Okay, did you get the same thing over here? Same, right? Same, right? So if you rearrange blah, blah, blah like that, so you will get that VA over RA plus VB over RB equals to the V plus RB plus RA. Wow, long. RA over RA RB. Okay, so the equation will be, I need one more slide. Okay, so your equation will be, you will get in the terms of V plus. Okay, so your V plus will be equal to, wow, long. So doesn't matter. So it is equal to the, you will get RA plus RVBA equals to the RA over R RA plus RBVB. Okay, you get the same thing over here. Okay, so your V out. Okay, so now you have equation. So now this is here. You have equation 1 and you have equation 2. Okay, you have to put 2 in 1. Okay, you will get this thing. Okay, V out. Okay, is equal to the 1 plus RF over R1. Okay, and then the whole terms over there times V1 B plus the whole things here RE over RE plus RB VA plus RA over RE plus RB VB. Yeah. So that's how you derive it. Okay. Yep. Like that. Okay, did you manage to get the same? But that's how you derive it, okay? So the tips is just applying KCL at, okay, previously you only apply KCL at one node, okay? Because the other node is ground, okay? So you apply KCL at one node, okay? In this case, so two nodes is active now. So you have to apply KCL at both nodes, okay? At nodes inverting and not non-inverting, and then you get the two equation. You'll be getting this. Okay, so is this kind of question will be asked in the final exam? Yes, the derivation. Okay, so the key to success is these two assumption. Okay, V plus equal to the V minus, and I plus equal to 0, I minus equal to 0, and finally apply KCL. All right. Okay, so the next one is difference amplifier or the subtractor amplifier. So you have to do again the same thing. Apply KCL at this node and KCL at this node. Okay, can you do it yourself? I leave it to you, and you prove that V out equal to V1 minus V2 R2 over R1. Can you do this on your own?
Okay, Doctor.
Yes, please. Okay, so the same method, the same assumption. Okay, all right. Now let's take a look on the exercise. Okay, so this is how it looks like. Okay, identify op-amp 1 means the name of op-amp 1. What is the name for op-amp 1? Where it is directly connected to the input. What is it?
Voltage follower.
Voltage follower. So op-amp 1 is voltage follower. Op-amp 2?
Inverting amplifier.
Yes, because you have negative here and connected to the input here. Okay, therefore, this is inverting amplifier. All right, so now let's let's calculate. Okay, for op-amp 1. Okay, for op-amp 1 over here, so it is unity of voltage follower. Okay, therefore this is V minus, this is V plus. Okay, V out 1 is equal to the V minus. In this case, V minus equal to the V plus equal to
1.5.
1.5.
yes, 1.5 volt. Okay, so V out 1 is equal to 1.5 volt. Unit, don't forget to put unit. Okay, 1.5 volt. My 5 is late. Okay. All right. So this node is 1.5 volt. Okay, so the next one is inverting amplifier. Okay, we have derived too many. For this one, I don't want to derive it again. Okay, it will take a longer time. So for the inverting amplifier, the V out is equal to the negative RF over R1 times V in, which is the V1. Okay, so I write down the equation here. Okay, therefore, V out here is equal to the negative RF over R1 times V in. Okay, what is RF here?
100K.
100K ohm.
Yes, the feedback resistor. What is R1?
20K ohm.
Yes, 20K ohm. Don't forget negative. Times V in. So the V in of op-amp 2 is equal to the V out of op-amp 1, okay, which is equal to the 1.5 volt. So if you calculate this, you will get entah. Can you find it for me? What is can you calculate? Did you get the yeah, we got the answer there. Yes. Here is the answer. Oh, this time too rajin and put the final answer. Okay. Negative 7.5 volt. Correct. Okay. So V out is equal to the negative 7.5 volt. All right. So let's move on the second exercise. Okay. Op-amp 1. What are the name for op-amp 1?
Voltage follower.
Unity follower or voltage follower. Whatever the name is, same. Okay. Op-amp 2.
Inverting.
Yes, because the input here is connected to the negative. Therefore, this is V in 2. This is inverting amplifier. Op-amp 3.
Non-inverting amplifier.
Yes, non-inverting amplifier here. Okay, because it is connected to the plus. Okay, Therefore, this is non-inverting. Okay, so now for the op-amp1, okay, op-amp1, op-amp1 unity follower. Therefore, V out1 is equal to the V minus. This is V minus. This is V plus. Okay, we know that V minus equal to the V plus equal to 0.2 volt. Therefore, in this case, V out1 equals to
0.2 volt.
yes, 0.2 volt. This is 0.2 volt at this node. All right, so let's solve for the op-amp2. So op-amp2 is inverting, okay, inverting. Therefore, V2 is equal to the negative RF over R1. Is it R1? Yes, times V in. Okay, in this case, V2 is equal to RF is 200K, negative 200K, over R1 is here how much? For the
20k.
op-amp2, yes, 20K. Okay, times V in 2 in this case equal to
0.2.
yes, it's the same note. Okay, so it is 0.2, right? So V2 is equal to, I hope my answer is correct over there. 2 volt. Can someone calculate for me?
Yes, same.
Yeah, same. All right, great. Okay, so V2 negative 2 volt. Okay, now let's take a look on the op-amp3. Okay, op-amp3. So op-amp3 is non-inverting. So we have derived the non-inverting just now. So non-inverting is equal to, where is non-inverting? Yeah, V out equal over V in RF over R1 plus 1. Okay, so that is for the non-inverting. Okay, so V out. Okay, so in this case, V3 is equal to the RF, okay, over R1 plus 1 V in 3. Okay, so your V in 3 is how much in this case? So this is your,
0.2.
yes, V in 3. It is connected to the same node here. Therefore, V in 3 also 0.2. Okay, so RF is 200K over R1 is 10K plus 1 times 0.2. I hope my answer is correct. Is it 4.2? Is 4.2 correct?
Yes,
Yes.
Yes. Okay, so this is how you do it for the exercise 2. Okay. All right, so this is a good exercise. So we name it everything. Okay, so op-amp1. What is the name for op-amp1? Op-amp1. So look at the input there. So input here connected to the plus. Therefore, this is?
Non-inverting.
Yes, non-inverting. Okay, non-inverting. All right. And then op-amp2, we name it first, op-amp2.
Unity.
Yes, unity follower. All right. Okay, so this is, I name it V out 1. Here I name it V out 2. Okay, here V out 3. Okay, for the op-amp1, okay, for op-amp1, V out 1, since this is non-inverting, so it is equal to the RF over R1 plus 1 V in. Okay, in this case, RF equal to what? 400K. R1 is 20K, okay, plus 1. So V in equal to what? So this is V plus, this is V minus. So V in here equal to V in at op M1 equals to
0.1.
yes, 0.1. Okay, so if we calculate here, oh, just final answer. Can someone calculate for me? V in 1, V out 1, sorry. 400K over 20K plus 1 times 0.1.
2.1 volt.
2.1 volt. Okay. And you, the rest get the same answer, 2.1 volt?
Yes.
Thank you. Okay. So for op M2, okay, so V plus equal to the V minus equal to, so V plus equal to the V minus equal to the V out 2 equal to, what is V plus in here?
0.1 volt.
Yes, the same node over here. Okay, the same node over here. Therefore, V plus is equal to 0.1 volt. So V2 also 0.1 volt. Okay. Okay. All right. So V2 also 0.1 volt. Okay. So V out 1 here 2.1 volt. All right. Now V out 3. Sorry, op M3. I forgot to ask. For op M3, what type of amplifier for op M3?
Summing
Summing
amplifier.
inverter.
Yes, summing, inverting or non-inverting?
Inverter.
Inverting.
Inverting. Betul. Summing, inverting. Alright. Okay, summing, inverting. Okay. Okay, so summing, inverting, we have derived it just now. So summing, inverting equal to the V out equals to negative RF times V1 over R1, V2 over R2, V3 over R3. Okay, so in this case, it has 3 input voltage. For this question, it has how many input voltage? It has only 2 input voltage. Okay, therefore, for op M3 in here, oh, I don't have enough space, but that's okay. So V out 3 is equal to negative RF. So it has 1 input here. Okay, so V1 over R1 plus V2 over R2. All right. So in this case, V out 3, your RF is how much?
100K.
100K. Okay. Times V1. In this case is V out 1. Okay. Equal to 2.1 volt. Okay. V2 in this case equal to V out 2. Okay. This is same node. Okay. V out 2, which is 0.1 volt. Okay, so V1 is 2.1 over R1 20K plus V2 is 0.1 over 10K. All right, so this is the final answer. Can someone calculate? Do we get the same negative 11.5 volt?
Same.
Can calculate for me? Same. All right, great. Great. Okay, same answer. So we have here negative 11.5 volt. All right. Okay. So this is for the exercise 3. So now exercise 4. All right. Okay. So you name it first. Okay. Okay, you name it first. Op M1. So what type of op amp for the op M1?
Summing inverting.
Summing, inverting. Correct. Okay. Op M2. Can I lazy to write? No. I
Unity.
will upload. Okay, summing inverting. No, don't be lazy. Summing inverting. Unity. The third one?
Summing inverting.
Again, summing. All right, okay. So you have to find for OPAMP 1, OPAMP 2, and OPAMP 3. Okay, so let's do it together. Okay, we are almost finished. Okay, so for OPAMP 1, I think if I write down OPAMP 1 top there, OPAMP 2 here, OPAMP 3. Okay, I think sorry, I write OPAMP 1 here. Okay, so OPAMP 1, this is summing. So summing, so here you have, I write down here V out 1. So here is V out 2. Okay, and here is V out 3. Right? So for this one, summing, okay, as you know that summing is negative RF, V1 over R1 plus V2 over R2. Right? So V out 1, negative RF is 600K, okay, times V1 in here. So this is V1, this is V2, okay. So V1 is 25 milli over R1 15K plus V2 is negative 20 milli over 30K. Can someone calculate for me what is V out 1? I put negative first. I'm waiting for the answer. So,
0.
is it
M 0.5 watt.
0.5?
5 watt. Wait. Okay.
Negative 0.5. Can someone calculate too for me, please? At least 2 people compare the answer.
My one is negative 0.6. Negative 0.6.
0.6.
Negative 0. All right. Okay. You also got negative 0.6. Thank you. Negative 0.6 volt. Okay. Over there. Okay. All right. Great. Thank you. So this is unity follower for the OPAMP 2. Okay. Therefore, V out 2 is equal to, so we know V plus equal to the V minus, V plus, V minus. So V plus now is how much? So V plus connected to negative 20 millivolt. Therefore, for the OPAMP 2, V out 2 is equal to the negative 20 millivolt. So this one, negative 20 millivolt. Okay. All right, for the OPAMP 3, so this node you have already V out 1, V out 2. So you have here V1 and then this is V2. Okay, it is the same thing, V1 and V2 over there. Therefore, this is summing inverting the same equation like here. Same equation. Okay, so therefore V out 3 is equal to the negative RF, which is negative feedback, 300K. Okay, if all the answer correct, your final answer must be correct too. Okay, so V1 in this case is V out 1, negative 0.6. Okay, over 30K. Okay, and V out 2, okay, V out 2, 20 millivolt equal to the V2, therefore minus 20 milli over 15K. All right, should be correct. Our answer.
Yes.
All right, great.
Yes.
Okay, great. Alhamdulillah, the same answer. All right. Okay. What is the answer? Sorry. Oh, 6.4 volt. Is it the same? 6.4 volt? The same?
Yes, yes.
Yes, great. Yes, okay. Okay, so you have done this, and this. So what you going to see in the your actual life? No, actual life. I mean, in the real situation. It could be like this as well. It could be this as well. Okay, instead of you have 1, 2, 3 op-amp, you have 5 op-amp. Can I leave this to you so that you can you can enjoy the question yourself? And we will get back with the final answer in the next class. Can you enjoy this on your own? Because there is the answer there, here, okay? So you have everything here for each op-amp. This is for op-amp 1, op-amp 2, op-amp 3, op-amp 4, op-amp 5. All right. Can you do it yourself? I think you can. All right. Great. Okay, all. Yeah, we had a very efficient day today. We finished part 1 of the amplifier of the op-amp. Okay, and we derived all. I have not left. I just left one with you, the subtractor or the differential amplifier. You derive your own, and this question. Okay, but I will get back this question with the final answer in the next class. Okay, I leave it to you. Okay. But first, name it first. Okay, all. I think that's all. Okay. If you have any question, you can ask me regarding the test. Okay. Everything you can ask me in the group. Okay. I will update to you for the test platform. Okay. I think I will do the same method as test 1 where I provide the Google form instead of e-learning. Are you all okay with that? Submission through Google form instead of e-learning. Is it okay?
Yes, Doctor.
Yes.
All right. Okay, all. Okay, all. Take care. I don't forget the tips that I've given you for the BJT. Okay, today, if you have 2 power supply and so on, I will upload the solution after this class. All right. Okay, all. I think that's all for today. Thank you all. Bye.